Alright, so we move on to using a rheostat as part of our potential divider. Now, you can see that if I use the same formula, and I'm going to call the potential difference across R1, V1. Okay, and potential difference across R2 is just called V out. So if I call this V epsilon, now, when R1 increases, what's going to happen? You know that when R1 increases, V1 is going to increase. And because this is a series circuit, V epsilon equals to V1 plus V2. So when V1 increases, now remember R is constant, right? So this one constant. So when R1 increases, V1 increase, it means that V2 must decrease since VA is a constant. V epsilon is a constant. So when V1 increase, when R1 increases, V out will decrease. Remember this V out is the same as V2, okay? Sometimes I forget and I say V2. It's the same thing. Alright, now what if R1 decreases? So when R1 decreases, your V1 is going to decrease. When V1 decreases, since V epsilon is a constant still, V2 is going to increase. So V out will increase when R1 decreases. Now when you use a potential meter can either be using a variable resistor or you can use like the ruler with the wire attached to it. Okay, now for that example of the wire attached to a ruler. Now because your resistance is proportional to length, why is that so? When you use R equals to rho L over A, for your entire wire, your A is a constant. And since you're using the same wire, your resistivity is the same. It tells us that R is proportional to length, right? So based on that, which of the following two circuits will produce a larger V out? Pause here and think about it. So when the answer would be circuit 1. Do you get that? Why is that so? Because when your resistance here is larger, it means that your potential difference across that resistance will be larger. Type 2, using a potential meter. Now, as what we've said just now, because your resistance is proportional to your length, now this equation over here is the exact same equation, just that instead of using R2, over here this is my R2, right? But my R2 is what is also the resistance of the wire between A to C. So that's why I call it RAC. And then this part here is like the resistance for R1, correct? So the resistance for R1, we'll call it RBC because that's the length from B to C. So this part here. So it's the same formula, but since we say that resistance is proportional to length, I can change this equation into instead of using ratio of resistance, I use ratio of length. So length AC to the length of the total length of the wire. Okay, pause here and try this question on your own. Alright, now the question asks us for maximum and minimum output voltages. So when will that happen? That will happen when your R1 is either 0 ohms or 100 ohms. Now, I may not know when my V out is maximum or minimum, so I'll just try it out first. When R equals to 0 ohms, I use my formula V out equals to R2 over R1 plus R2 times your total V. What's my V2? 50. R1 is 0 plus 50 times 9. So what you get? You get 9 volts. Now when my R is 100, oops. Okay. When my R is equals to 100 ohms. Okay, let me do that again. R equals to 0 ohms. So V out equals to R2 over R1 plus R2 times total V. 50 over 0 plus 50 times 9, that gives us 9 volts. So when R2 is, this is R1. when R1 is 100 ohms, so V out equals to R2 over R1 plus R2 times total V. R2 is 50, R1 is 100 plus 50 times 9. What do you get? You get 50 divided by 150 times 9. You get 3 volts. So this is our minimum V, this is our maximum V. And you can see that minimum V happens when your R1 is the largest, right? Which makes sense because when R1 increases, it means that V1 increase. When V1 increase means V out decrease. Okay, that makes sense. Okay, so this is what I've just gone through. Now let's talk about input transducers, or what are transducers in the first place? Okay, so transducers are electronic devices that converts energy from one form to another. So there are two types of transducers, input transducers and output transducers. Now for input transducers, what do? They change non-electrical energy into electrical energy. Examples of this will be thermistors, LDRs, microphones. Microphone, right? From sound into an electrical energy. Okay, what about for output transducers? They change electrical energy into non-electrical energy. So like your loudspeakers, your lamps, your LEDs. Okay, not lamps, but yeah, LEDs. Okay, so input transducers basically responds to changes in the physical environment. And then they are used in potential dividers to vary output voltages. Alright? So one example would be the LDR. Turn to page 232 of your textbook, please highlight that there. For your LDR, the most important thing that you need to know is that when light decreases, resistance increase. When light increases, resistance decrease. So basically the relationship is the opposite. Alright? Now, so let's talk about when light decreases. When light decreases, we say that the resistance of the LDR will increase. When the resistance increase, what happens to the voltage across it? The voltage across the LDR will increase. When the potential difference across the LDR increase, it means that my potential difference, my V out here will decrease. Alright? So we use this to measure light intensity in automatic street lamps. Try this out now and pause here first. Okay, so describe how the voltmeter reading changes as the light intensity decreases. State a suitable use for this circuit. So they tell you that light intensity decrease. So when light decrease, resistance here will increase. When resistance here increase, it means that potential difference across it will increase. Now, we're talking about light decrease, right? If light decrease and potential difference across it increase, what do you want to happen? You will actually connect maybe your street lamp on this side here, so that when it's dark and your potential difference across this component, this junction here increases, you want your light, your street lamp to light up. Okay? Now, what about for thermistors? So the main thing, lesson on page 186 of our textbook, the main thing about thermistors is that when temperature increases, resistance decrease. So again, it's an opposite relationship. So how does a thermistor look like? Oh, sorry, the symbol. Okay, the circuit symbol looks like this. This is important. You need to be able to recognize it. So I forgot to mention about LDR. For LDR, it will look like this. You have this circle with like a resistor, and then they normally draw the arrows here to show you that it needs light. Okay, so for thermistor, it looks like a resistor, but it has this line here. Alright, going across it. Okay, so let's try example 4. Sorry, let's go back first. So when temperature decreases, so say temperature, when temperature increase, we say that the resistance across the thermistor will decrease. right? So when the temperature, so when the resistance decrease, my potential difference across the thermistor will also decrease. When potential difference across the thermistor decreases, my V out will increase. All right. Now, by the way, your V out is really depending on where you choose it to be. I can always choose my V out to be here. Okay, and then if that's the case, then my V out will just decrease when my temperature increases. So depending on where you choose your V out to be. Okay, let's try example 4. So what's the correct answer? A. Do you get that? Now they tell you that thermistor heats up. So when temperature increases, your resistance across the thermistor is going to decrease. So when resistance across the thermistor decreases, it means that my potential across the thermistor will decrease. When potential difference across the thermistor decrease, it means that potential difference across this part here will increase. There you go. Try example 5, pause here. Okay, so question asks, in which circuit will the bulb glow more brightly when less light shines on the circuit? So when we talk about less light shining, am I making use of a thermistor or an LDR? LDR, right? So the ones with thermistor I can cancel out. So for LDR, let's look at option C. So when light decreases, it means that resistance increase. When resistance increase, it means that potential difference across the LDR will increase. When potential difference across LDR increases, it means potential difference across this part here will decrease. If potential difference across this second part here, the resistor here decrease, it means that my bulb here, having decreasing potential difference, will become dimmer. But they want the bulb to glow more brightly, so C is wrong. Now let's look at D. So same thing, when light decreases, resistance here will increase. Resistance here increase means potential difference across the LDR will increase. When potential difference across LDR increases, if my bulb is connected across the LDR, it means that potential difference across the bulb has increased. And when that happens, it means that my bulb will become brighter. So answer is D. Okay, we will end here. That's the end of the chapter. You can continue with this to learn more about transistors, but this will not be in your syllabus for IGCSE. So what you need to do now is to complete your worksheet, and we will go through the answers the next lesson.